Fire control computers solve fire control problems. Their solutions depend upon own ship's course and speed, target's range, target's bearing, target's course and speed, wind speed and direction, initial shell velocity, and other factors up to a possible total of 25. The factors occur simultaneously, and many are constantly changing. But the computer continuously and instantly solves the problem and sends the answer to the guns as train and elevation orders. A computer cannot do this without men. For example, men operate the director, which sends target range and bearing to the computer. And here at the computer, other men set in other information. Obviously, computer accuracy depends on the quality of the information it receives, and that depends on the skill and understanding of the men. If you look inside a computer, you find an impressive assembly of basic mechanisms. Some of them are duplicated many times in one computer. A first step toward understanding a computer is understanding these mechanisms. This film, Part 1, describes 4 of them. Shafts are commonly used to carry values throughout a computer. One revolution of a shaft is assigned a numerical value. If rotation in one direction is designated as positive, then opposite rotation is negative. The nature of shaft values can be demonstrated with a rack and pinion. In this case, the rack is calibrated, so that one revolution in this direction represents plus 10. Continuing with a half revolution, shaft value now is plus 15. Another half revolution, making a total of 2 revolutions from the 0 position, and shaft value is plus 20. Now add minus 2 by 1/5 turn in the opposite direction. The result, of course, is 18. Similarly, 2 complete revolutions in the minus direction subtract 20. And in this case, the result is minus 2. The rack and pinion were used here to demonstrate the nature of shaft values. In practice, racks and pinions may be used to translate shaft values to corresponding linear movement. Or the rack may transmit values to the shaft. Gears are usually used to transfer values from one shaft to another. With a gear ratio of 1:1, the numerical value remains unchanged, but rotation is reversed. With gears of different sizes, shaft values may be multiplied or divided by a constant. With this gear ratio of 2:1, one revolution of the driving shaft causes 2 revolutions of the driven shaft. Cams may be used as computing mechanisms. Ordinarily, we think of a cam as a mechanism that changes a simple motion, such as rotation, to an irregular or intermittent motion. All cams have a working surface and a follower. The working surface may be an outside edge like this, or it may be the walls of a groove. The follower may be a roller, a ball, a pin, or some other device that slides or rolls on the working surface. Different working surfaces are designed to do different jobs. To show in a general way how working surfaces are designed, suppose we take as an example the problem of changing rotary motion to corresponding linear motion. Let's say that one shaft rotation is assigned a value of 10. For a shaft value of 1, suppose we want the follower to move this distance. Then for a shaft value of 2, the follower must move twice as far. 3 times for 3, and so on. The purpose is to establish the shape of the working surface for this particular problem. The principle becomes clear when we add a representation of a follower and a scale. 4 on the shaft, 4 on the follower. The same with all other values, not only for whole numbers, but for all values in between. With an outside shape as the working surface, the capacity of such a cam is limited to 1 revolution. Additional revolutions can be obtained by extending the working surface, which now must be a groove. An example is the constant lead cam, where the follower is a pin riding in the groove. In a fire control computer, a rotary input of ship's speed is delivered as linear of the follower. In the reciprocal cam, the output is equal to 1 divided by the input. The working surface is constructed by plotting points on radii. This distance on line 1 represents 1. Half this distance on line 2 represents the reciprocal of, or 1/2. 1/3 on 3, and so on. With this curve cut as a groove in a disc cam and a follower added, the cam output will be the reciprocal of any input. Let's watch it. Disc cams generally have a non-computing runout at both ends of the plotted curve. This is a square cam, so called because it delivers the square of an input, which may be either plus or minus. The tangent cam is an example of a trigonometric cam. In this cam, the input can be any angle between 40 and 70 degrees. The output, the tangent of the angle. This time of flight cam is an example of a flat ballistic cam. The working surface is the outside contour of this part. The input is range. The output, time of flight. This is a sector-type follower, held in contact with the cam by a spring. You can see how the cam turns the output gear. A barrel cam, also called a three-dimensional cam, computes from 2 different inputs and delivers 1 output. The barrel shape is the working surface. This is the follower. The example shown here computes super elevation. Briefly, the problem is this. Gun elevation is the sum of super elevation and advance elevation of the target. Super elevation increases as advance range increases, but not in direct proportion. Super elevation decreases as advance elevation increases, again not in direct proportion. Thus, super elevation is determined by advance range and advance elevation, both of which are the inputs to this cam. The output is super elevation. The mechanism can be understood if you first consider the super elevation problem at one elevation only. There can be any number of ranges, and each range requires a different super elevation. In a cam cut for one elevation only, and the range input positions the barrel for the required range. The principle of the barrel cam is as simple as this, although in application it may appear quite complex. Differentials are used in computers to obtain continuously the algebraic sum of two quantities. These quantities represent the inputs. As the inputs vary, the differential simultaneously delivers the answer, no matter how rapidly the inputs change. This is a bevel gear differential. There are other types, but we are using this as an example because of its frequent use in fire control computers. To understand how it works, it's necessary to know something about its construction. Remove the gears, and you see two shafts. They are solidly joined together. The shafts and these gears form an assembly called the spider. These are the spider gears. This is the spider shaft. And these are end gears. None of these four gears is fixed to its shaft. Each gear is freely mounted on bearings as shown in this cutaway. Connections to other mechanisms are made through spur gears. One lock to each end gear and one lock to the spider shaft. Additional gears and shafts complete the connections. Although there are two spider gears, only one is needed for the mathematical problem. The other is there to balance the mechanism. So we can remove one spider gear, and we now have the basic elements of a differential. To study its operation, it is necessary to count and compare revolutions of the end gears and the spider shaft. That isn't easy to do. We'll show the differential action in a way that's easier to follow. Essentially, this differential is a gear between two gears. Now imagine that you cut the end gears and make them flat. You now have a pinion between two racks. The operating principle is the same as the bevel gear type. Either rack, A or B, or the pinion may be used as the output. The other two parts then are inputs. We'll use the pinion for output, the racks for inputs. Now let's examine the mechanical action. Motion will be plus or minus, measured with reference to the 0 point. Move A 4 inches in a plus direction. and B 2 inches. The sum is 6 inches. Note that the pinion center has moved 3 inches, or half the sum of the rack displacements. When A is at 1 and B at 3, the sum is 4 inches, and the pinion center is at 2 inches. As another example, move A to minus 4 inches and B to plus 2. The algebraic sum of the rack displacements is minus 2 inches, and the pinion center has moved to minus 1. Measured from 0, the change in the position of pinion center is always half the algebraic sum of the rack displacements. Because of this relation between rack and pinion movements, a differential can be used as a computing mechanism. Instead of inches, we assign a desired scale of values to the racks. Then, with half that scale for the pinion indicates the algebraic sum of the rack values. 3 plus 1 on the racks, 4 on the pinion. Plus 1 and minus 2, minus 1 on the pinion. Plus 3 and minus 3, 0 on the pinion. There is no fundamental difference between the rack and pinion differential and the bevel gear type. The racks, which are limited in length, are replaced by end gears, which serve as endless racks and handle values in the same manner as do shafts. The pinion is replaced by the spider gear. Movement of the spider gear center along its circular path is delivered as rotation of the spider shaft. Adding the second spider gear to balance the mechanism, we now have the complete differential. It should be remembered that the output may be either one of the end gears or the spider shaft. The other two then become the inputs. Understanding the component solver depends on some understanding of the kind of problem it solves. As an example, we'll use this simple situation. The target is stationary, and own ship's course and speed are constant. With the ship's movement, range changes continuously. Target bearing, too, is always changing. Furthermore, not only are range and target bearing changing, but the rates at which they change are not constant. To illustrate, these 4 ship positions are spaced at equal intervals of time. During the time between A and B, the change in range is greater than it is during the time between C and D. Thus, the rate at which range changes is not constant. And note, too, that between A and B, the change in target bearing is less than it is between C and D. Thus, the rate at which target bearing changes is not constant. Solving the fire control problem requires continuous information of the existing rates of change. This is a vector problem in which we know own ship's course and speed, shown here by the length and direction of its speed vector. We also know the line of sight to the target. The rate of change in range, or range rate, is the component along the line of sight. The rate of change in target bearing, or bearing rate, is the component perpendicular to the line of sight. Comparing vector diagrams at two ship positions, the difference in the components of bearing rate, and also the difference in the components of range rate, show again how these rates may change, even though ship's course and speed are constant. These rates also change with a change in course. They also change with a change in speed. The problem is how to provide continuous, up-to-the-moment solutions. This is done by the component solver. It continuously forms the vector diagram, measures the components, and transmits their values to other parts of the computer. To see how it forms the vector diagram, we'll start with the speed vector, considering first its direction. Direction is measured relative to this center line, which represents the line of sight. The speed vector lies along the slot in the vector gear. An input gear turns the vector gear. Direction of the slot relative to the center line reproduces the direction of ship's motion relative to the line of sight. Now let's see how vector length is obtained. Under the slotted vector gear is a cam. The cam surface is a spiral groove cut in the face of a gear. The cam is positioned by this input gear. A follower, with a projecting pin, rides in the groove. The pin extends up through the slot in the vector gear so that pin and follower can move only along the slot. Ship speed is entered through this input gear. With a transparent vector gear, you can see how the spiral groove moves the follower and pin along the slot. The distance from gear center to pin is the length of the speed vector. When the speed is 0, the pin is at center. At low speeds, the distance from pin to center, the vector length, is small. As higher speeds are introduced, the vector increases. The vector is maximum when full speed is reached. Now that we know how the speed vector is produced, we next want to see how its components are obtained to complete the vector diagram. For this, there are two slotted racks, with the pin extending up through both slots. As the pin moves to form the speed vector, it also moves the racks to form the vector's components. To show this clearly, let's observe one rack at a time. Starting at 0 position, notice the rack movement as the pin moves into position to create the speed vector. The distance moved by the rack is equal to the range rate component along the line of sight. To show how this component is measured and is transmitted as range rate, return the rack to 0 position. Now watch this output. Output rotation measures the amount of rack movement, or component's length, and through the output shaft transmits the measurement as range rate to other parts of the computer. The other rack works the same way, but its movement is perpendicular to the line of sight. This component is bearing rate, and its value is transmitted through this output. When own ship's course is along the line of sight, the bearing rate component becomes 0. And the range rate component is equal to the speed vector. At 0 speed, both racks cross at the center, and the outputs are 0. This is a disk-type integrator, one of several different types. They can do many jobs. One of the simplest, the job in range keeping, will give you a pretty good idea of what an integrator can do. An elementary example of range keeping is one with stationary target and with own ship moving at constant speed along the line of sight. The problem starts with an observed initial range. At any moment, the sum of range change and initial range is present range. If own ship is moving toward the target, present range is obtained by subtracting range change from initial range. In this case, range change is a minus quantity. In the other case, a plus quantity. Present range, then, is the algebraic sum of initial range and range change. A disk integrator computes range change. So let's examine this part of the range-keeping problem. Starting again at the initial position and with range changing at a constant rate, say 10 yards a second, it's easy to see that after 10 seconds, range change is 100 yards. After 20 seconds, 200. After 30, 300, and so on. But what was the range change at all other points? With ordinary arithmetic, you couldn't keep pace with this problem. And of more significance, the solution would be in a series of jumps. Range doesn't change this way. The integrator computes range change like this, smoothly and continuously with the changing range. This example, with range changing at a constant rate, was used here because of its simplicity. Actually, in almost all situations, range change is not constant. Nevertheless, the integrator continuously computes range change and delivers it as an input to a differential. The other input is initial range. The differential delivers the algebraic sum as present range. Keeping the problem in mind, let's turn now to the mechanism itself. With the top raised, you see most of the basic parts. roller, a disc, and a ball. There's another ball onto this one, and both are held in a carriage. These parts are shown here in schematic form to demonstrate operating principles. There are two inputs, and both are held in a carriage. These parts are shown here in schematic form to demonstrate operating principles. There are two inputs. One input is time. It is represented by the disc which is motor-driven at constant speed. The other input is range rate. Range rate, coming from component solvers, moves or positions the balls like this. Range change is the roller's position measured in revolutions from its starting position and transmitted through an output shaft. The rotating disc, through friction, turns the balls and the roller. When the balls are near the edge of the disc, the roller turns at maximum speed. Roller speed decreases as the balls approach the disc center. And, at center, roller speed is 0. In principle, the roller and disc are comparable to a variable gear ratio, where the circumference of the roller and the track on the disc act as two gears. The balls act as idler gears. The circumference of the roller and of the balls, of course, is constant, but the track on the disc is variable. This is the equivalent of an infinite number of gear ratios. To make the mathematics easy to follow, suppose the disc turns 1 revolution per second, which we will show on this time counter. And at the output, suppose that 1 revolution of the roller represents 1 yard of range change. Range change will be shown by this counter. Then, with a range rate of 3 yards per second, this input places the balls in position for a disc-to-roller ratio of 3:1. The roller now turns 3 times for each revolution of the disc, and range change accumulates at the rate of 3 yards a second. A constant range rate is unusual. In most situations, range rate is always changing. This may be regarded as a progression of range rates, infinite in number, and with the integrator continuously computing each instantaneous change and adding it to the total output. There's one more point. The roller turns in one direction when the balls are this side of disc center, and in the opposite direction when they are on this side. One side is designated for plus range rates, with the output adding range change to initial range. The other side then is used for minus range rates, with the output subtracting range change from initial range. Thus, with any range rate, high or low, plus or minus, the integrator continuously multiplies range rate by time and delivers range change, which is the effective sum of all changes. Multipliers are mechanisms which can multiply two continuously changing values. We shall use this rack-type multiplier for purposes of illustration. Other types work on the same principle. The rack multiplier has two input racks, A and B, at right angles to each other, and an output rack. One input rack has a slotted pivot arm, which swings around a stationary pin. The other input rack has a slot which is engaged to the pivot arm by a sliding pin, called the multiplier pin. When either input rack moves, it changes the position of the multiplier pin. This pin also engages the slot of the output rack. So movement of the input racks positions the output rack. When the multiplier pin is lined up with the stationary pin, both input racks and the output rack are in zero position. To make it easier to see how this mechanism operates, let's put appropriate scales along each input rack and along the output rack. The values are plus in one direction and minus in the other direction. Now let's see. With an A input of +2 and a B input of +3, the output is 2 times 3, or +6. Or with inputs of +4 and +4, the output is +16. Now let input A remain at 4 and change B to 0. The output is 4 times 0, or 0. When one input is 0, the output always is 0, regardless of the other input value. Now, with one input a minus value, say -3 times +4, the output is -12. With both inputs -2 times -4, the output, of course, is +8. Thus, the multiplier handles both positive and negative values. It instantly delivers the product of any two input values, even though the inputs are continuously changing. The reason why the output of this mechanism is the product of the two inputs can be shown geometrically. Starting with the multiplier pin centered over the stationary pin, we'll use this line as a baseline. The distance along this line from the stationary pin to the pivot pin is a constant. Let's call it K. Let's assume input A moves distance A, and input B moves distance B. Let's call the length of the output X. Now, a line along the slot in the pivot arm forms two similar triangles. Their corresponding sides are proportional. Therefore, X is to B as A is to K. Multiply both sides by B, and we get X equals AB over K. In other words, the output X equals the product of the two inputs divided by K, a constant. Distance K is always a constant value in each multiplier, and its effect is taken care of by proper choice of input and output gearing. Only 7 mechanisms were described in parts 1 and 2 of this series, and we have spent only a short time with each mechanism. But it was enough to indicate how mechanisms are used for computing, and how, by studying the mechanisms separately, you can gain much understanding of the instruments which solve the fire control problem.